Morning, good afternoon, everybody. My name is Eric Novik. I'm your host, and I'm excited to have Kristian Brock join us here from the UK. Welcome to the program, Kristian.
Thank you very much. Thanks for having me.
Excellent. So before we jump into your talk, you and I chatted a bit before this, and you mentioned, just like me, you hated your first statistics class. You hated it so much you dropped it, and I hated mine so much I almost failed it. And so from these beginnings, how did you come around to stats as your field?
Yeah, it's actually true. I was really not far into an undergrad degree at University of London, and I just hated learning how to calculate sums of squares of residuals for ANOVA tables. I just thought, this is so dull. And I dropped stats as soon as I could. And I went off to work I got a job out of university in the City, which is like the UK version of Wall Street. And I was put into a quantitative team. And there I was working amongst people who generally had PhDs and at least master's degrees. And I realized I just had this master's degree, but I had no practical data analysis skills. So I kind of limped on for a few years. But the financial meltdown and 1 in 3 jobs was sort of lost in the City in sort of like 2008, 2009. And my job disappeared. So I had to go back, and I thought, well, now seems like the time to go and get the skills I should have had 10 years ago. So I went and did a master's degree in stats and there, got taught some good Bayesian stuff, and that sort of turned it around.
Yeah. So how the Bayesian thing in particular, is that just an accident of you encountering it in grad school? Or?
So I went to the University of Sheffield, and they have a good focus on Bayes. They have a dedicated module, which is compulsory for the MSc in stats. You do a Bayesian module. It was still teaching bugs when I was there, but I'm reliably informed they've switched to Stan now, I think, which is good. But yeah, just the Bayesian way of doing things really appealed. I think also just because I've always been, since I was a kid, like a bit of a guy who likes tinkering around with computers and programming computers, and that Bayes just sort of felt very much towards the computational end of statistics. So it just sort of naturally appealed to me. And then afterwards I've got jobs like at a trials unit and now at a pharma company, and they have strong sort of onuses on using Bayesian methods. So it's just kind of grown from there, really. Yeah.
So you have a fairly recent PhD from University of Birmingham. So congratulations. It's a long road, I'm sure. In the program there, it's called clinical trial methodology, which sounds like, is that like a dedicated program for clinical trial, or it is something that you chose as a specialization?
Do you know what that is? I came up with that phrase. There's no program. There was this form I had to fill in one day, and so I was a little bit of an aberration. And then I did my PhD in parallel to working full time in a trials unit. And naturally, you're working in clinical trials, you're going to be doing clinical trial methodology. But I didn't quite fit into any of the departments. I didn't study inside a stats team or a math department. I studied sort of on the side whilst working as a trialist, and that meant I was always I'd go to fairs where people the postgraduate fairs where all the students had to present their work, and there would just be I was basically in the School of Cancer Sciences, so there were loads of people talking about the biology and the cell signaling, the mechanisms of action and inhibition and things like this, and then I'd get up and talk about trial design, and everyone would be like, who's this guy? So when I came to fill out the form, I just it said, I had to give a topic. I was like, clinical trial methodology, and it kind of stuck. So I basically went.
That's great. Now, so you've got your PhD, and then you finally decided to go to the dark side. I don't know if I can say. And you joined the pharma industry at UCB, which, for those of us who are not familiar with pharma industries, I believe a Belgian pharmaceutical company. Since your experiences are quite fresh, I'm wondering, what are some of the immediate kind of impressions and differences between the academic work and the kind of things you're doing at UCB?
The biggest difference is the workload and the focus. So in academia was a great place to work. I really enjoyed it, but everybody who was working in it was always overworked. And I think that's because academia tends to be its own worst enemy, in that people do teaching, they have to do their own research, of course, they have to apply for grants, most of which don't get funded. Some of the work that goes into a grant can be recycled, but it seems like everything that comes along, you're sort of expected to do all of it. And I guess there was another element that I was working in a trials unit, so delivering the trials was the main thing. And without sort of realizing it, I think I just spent a number of years just going from one thing to another, like keeping all these plates spinning, but never really letting any of them drop, but never really doing any of them to any fantastic level. Going over to pharma, the things I work on, it's much more focused. There's no onus to go and do things like speaking or really teaching, any of that stuff. You can sort of do it if you want to, but it would be absolutely fine for me to just focus on the methodology of research that I'm doing. So when you came calling and said, would you like to give a talk? I had to think, well, do I have anything to say?
I'm sure we'll learn in a little bit that you, in fact, do have something to say. I had first time I heard you talk at StanCon in Helsinki. I liked it quite a bit. Okay, so why don't we jump right into it? Kristian is giving his talk. Feel free to type in some questions in the chat. I will collect these questions and then we'll ask those at the end of Kristian's talk. So Kristian, take it away.
Super. Okay, so thanks for the invite and thanks for coming to my talk. Those of you who are here, I realize there's a big event going on in the US right now, so I appreciate you coming to listen to me rather than to see a guy in bullhorns try and take the Capitol for the second time in 2 weeks. So my talk's on functional uniform priors within the realm of dose finding models, and dose finding models dose response models tend to be non-linear in nature. So specifying priors for them, there's a few sort of twists in the tail there. What I'm going to do, I'm going to dive right in and just give an introduction to the types of data that these models tend to be fitted to. So classically, dose response data sort of looks like this. It's got this classic S-shaped curve to it. If I was to sort of like break down what I mean by that, just to remove any ambiguity, I'm going to say, let's take just the leftmost set of points that I've highlighted in red and consider just only those, ignoring all the rest for now. If I was to fit a line of best fit to those, the gradient of the line would probably be 0 or close to 0, basically suggesting that as dose is increased, of course, the x-axis here is dose. As dose is increased, the y-axis, the response variable, doesn't really, under expectation, it doesn't really increase. Well, if I was to shift my way along a little bit and to have a look at the sort of middle section of doses and just look at those points there in red, and if I was to do the same thing, we'd very much get a line that had a positive gradient, suggesting that as dose is increased, the expectation of y is increasing too. But then, of course, in the latter third, there comes this bit where you get to high enough doses that if I was to repeat the exercise, I'd probably get a gradient of 0. So putting all of those bits together, you kind of get this classic S-shaped or sigmoidal fit. And that particular one there is using a logistic model, and I'm going to say a little bit about that later on. One of the first points I want to make early on is that the x-axis dose is actually quite well. Both of the axes here are quite flexible in that you can sort of interpret them in different ways. And now that I've started working on these problems, I start to see them everywhere. So dose, the x-axis could of course be dose, the amount of milligrams of a drug that we put in someone's mouth or inject into them. It could be something like exposure, so the amount of a molecule that makes it to a target tissue, like serum, for example. Or it could be exposure in a bit more of epidemiological sense. So when I was young, there was this pet hypothesis. I was too young to really know too much about it, but I remember hearing somebody speculate maybe incidences of childhood cancer are linked to living close to power lines, to pylons. And in that sense, the distance to a pylon or how long you've lived there could be sort of interpreted as some kind of exposure if you're doing an epidemiological study. Going back to the sort of more trialsy interpretation, intensity, it could be the intensity at which a treatment's given, even if the dose is broadly kept the same. Or of course, it could be duration. So do we treat somebody for 3 weeks, 5 weeks, 8 weeks? So there's lots of different ways that X variable could be changed that all sort of like map onto variations of this idea that we're giving more or less of some kind of treatment. And of course, there's flexibility in the y-axis too. So this data set here is obviously continuous. You can see that from the points. But of course, that could be a binary event. There could be a yes-no variable for each patient. And in those circumstances, that blue line there, the line of best fit, would be interpreted as the probability of the event happening as the dose is varied. And of course, sitting between binary and continuous, you've got count variables. So it could be something like a Poisson variable, or how many days in a month do you have headache, something like that. So there's a lot of flexibility there. And since I've started working with these models, I've started to see applications for them in lots of different places. So I'm going to dive in with an actual model, the Emacs model. To people who work in this field, they'll know instantly what I'm talking about. And to everyone else, the Emacs model it's a very common dose response model. And it looks like this. So X is the dose that we give to somebody. Theta is, of course, just a vector of parameters. There are 3 parameters in this version of the model. And mu x theta just models the expected response in a patient that's given dose X. Now, over the next couple of slides, what I'm going to do, just for the sake of exposition, I'm going to say, pardon me, let's say that theta 0, we're just going to give it the value 0, okay? And we're going to set theta 1 to be 1. So those first two terms just essentially disappear. And we're going to consider X on the region 0, 1. So that's basically saying whatever doses we're giving in a trial, we scale them down to just 0, 1 by, dividing through by the max and shifting it by the min if you want to, or something like that. I'm also going to say, let's treat the response variable so that it's binary, 0, 1, so that the mu x of theta in this circumstance will be interpreted as the probability of the event happening in patient I, okay? Now, I should say all of these assumptions I'm just making to make things simple for the next few slides, but of course they can all be relaxed without problem, and we'll see some of those assumptions relaxed later on. But let's just say, for now, let's get tangible with the function and say, let's visualize the function subject to those points in the bullets, with setting the parameter theta 2 to be 2, fairly arbitrarily. First thing to say about the axes is that they are plotted focused in on the scale we want. So dose goes between 0 and 1, so the x-axis is only showing between 0 and 1, and y, of course, is binary, and so the response curve is a probability, so of course that maps to 0, 1. So this unit square represents the function space that we're operating in. And you can see there we get this curve, the Emacs curve, if we could call it that. Is quite kind of linear, but it is sort of shallowly decelerating. Let's just go 1 unit in either direction. Let's also look at 1 and 3, just to explore really how this function behaves with respect to the parameter, bearing in mind that what we're ultimately going to be building up is a prior for the parameter. And if you step 1 unit in either direction from 2, you get these curves in red and blue. And the main point here is that this distance here is much greater than this distance here. So uniform steps in the parametric scale don't map to uniformity in the function space, as it were. And really, to really generalize that idea more fully, I said, well, let's take a uniform distribution on the parameter and calculate those deciles. So the deciles on the region 0.5 obviously correspond to 1/2, 1, 1.5. And so these sort of represent the functional deciles, if you like. And what this prior, if I had this prior, what I'm saying is I attach only a 10% prior chance that the function occupies this space here, but 90% chance that it occupies this space here. And as I move through the deciles, those function instances get more and more bunched up. So really, they're not covering the function space at all well. It would be much sort of more intuitive. It would be more appealing, I think, if we had a prior that kind of explored this region and less of this one. Basically, the answer is, or an answer is, this field called functional uniform priors by Bornkamp. To illustrate his method, I just said, let's just decompose mu down to its nonlinear and linear parts. So this function is linear in theta 0 and theta 1, and the method that I'm going to introduce will do nothing for parameters in which the function is linear. So I'm just going to get rid of those. I'm just going to focus on the f aspect. This is the nonlinear part of this function. So Bornkamp's method, it says, okay, so we've got a set of doses under investigation, and that's x. And let's say we've got 2 parameterizations of this function f, and those different parameterizations could be labeled theta and theta primed. And what he said is, what I want is a metric to measure the distance between 2 functional instances. So of course, those 2 instances map onto functions f of x theta and f of x theta prime. And really, the distance between those 2 instances can be calculated using this metric here, which, as you can see, takes it calculates the square difference between the functions whilst integrating out the effect of x, so averaging over the entire span of doses I'm interested in. And then, of course, the standard deviation term takes us back into the units that we were originally in. In Bjorn's paper, which I give the references at the end of the slide deck, what he shows is that we can use a Taylor series expansion to derive this expression, this approximation here. And as is fairly standard in these types of things, we've got these higher order terms here that are going to be relatively small. We've got the main kind of bit over here. Now this introduces a few new guys, a few new characters. So the integral part is now encapsulated in this matrix called Z star. And that itself involves this object called Jx of theta. And that's just a vector of the partial derivatives of f with respect to each of the elements in theta. So J has as many elements as there are elements in theta. So in my Emacs example, where I had just one nonlinear parameter, J of x is just going to be a single a single function. But if there were two elements in theta, then J would be 2 elements long, Z star would be a 2 by 2 matrix. Bjorn shows in his paper is that this object that he calls the functional uniform prior is proportional to the square root of the determinant of this Z star matrix. He proves that in his theorem 1 in his paper, and I'm probably just going to leave it there with the technical details. Of course, you can go and get that and satisfy yourselves about what on earth's going on. But some real points I wanted to make about this are that calculating P of theta obviously involves a fair bit of calculus. If I just skip back to the last slide, it involves calculating this vector of partial derivatives. That's no problem at all. But this bit here, where you're integrating out with respect to dose, having differentiated with respect to the parameters, calculating the Z star can get quite involved. So there's a fair bit of mathematics there. And it's not really for the faint-hearted. It's not the kind of thing you do for fun, I don't think. Another point I want to drag out here is that theta, like I've said, can have several elements to it. Well, P of theta is the joint prior. So really it can be interpreted as some kind of probability surface, depending on the dimensionality of the problem. And lastly, of course, the P of theta are generally non-standard distributions. You don't do the maths here and then outdrops, the normal density or a beta density. What tends to come out of it is, some pretty awkward looking functions, polynomials. They're all, the 4 examples I'm going to introduce all produce analytic solutions, but they tend to involve exotic creatures like the digamma and trigamma functions and the dilogarithm. So they're not necessarily pleasant things to work with. But of course, Stan handles all of that stuff with aplomb, and that's something I'm gonna talk on. Coming back to the Emacs example, I want to demonstrate the functional uniform prior applied to this relatively simple example. So here is the f, just as a reminder, x over theta 2 plus x on the region 0, 1 for dose. If we apply Bornkamp's method, what we discover is that the functional uniform prior for the theta 2 parameter is equal to 1 over the square root of a quartic, so effectively 1 over a quadratic, and that's fine. So we can go ahead and plot that density, and we get this. The first thing to say there is how dramatically different this is to a uniform density. If you were shown that distribution and asked whether it was informative or uninformative, you'd say it's highly informative. It's saying that parameter values around 0 are much more likely than high parameter values. In fact, what this density curve is saying is that you don't really need to entertain any thought that the theta 2 parameter is greater than 3. There's just no probability mass over here at all. In fact, there's very little greater than 2, and all of the action is over here. That's good. That at least marries up with the intuition that what we needed, where we were going wrong with the uniform prior, was that we were putting too much weight on these high values of theta and not enough over here. And this would seem to rectify that. But let's repeat the exercise we did before and have a look at the deciles. So if we calculate the deciles for that distribution and plug that gives us these values here in the legend. And if we plug each of those values in, we get the accompanying set of function forms. So as we can see, we're exploring the function space much more convincingly now. There's a good coverage of the functional shapes, and we're also getting this much more uniform spacing, and that there's generally a finger's width, should I say, between each of those functional deciles as we make our way down here. So we would seem to have achieved what we set out to do. Bornkamp's method works. Just to really nail home that point, here's side by side the original plot I showed you of those functional deciles corresponding to a uniform prior alongside those equivalent deciles from a functional uniform prior. And you can see, it's really clear here that we're much more convincingly covering the functional space. Now, this raises an interesting point. Here I am arbitrarily talking about the region 0, 5. What if I was to change that region and swap it up to, say, 0, 10? Well, repeating each of those methods, we get the following plots. And if I flip between the previous slide and this slide, what we can see, focusing on the left-hand side first off, is that the problems have been exacerbated. And of course, there's an intuition to why that's happened. We've put yet more prior mass on these large values of theta 2 that produce these curves that don't tell us much. So all of these curves have been shifted downwards, and we've exacerbated the problem. In stark contrast, looking at the right-hand side now, the functional uniform priors, or the deciles that are generated by the functional uniform priors, don't really look that different at all. If we look at the labels, you can see that they are shifting a bit, actually, towards the upper end, but towards the lower end, they're really not shifting at all. So that sort of tells us as well that this functional uniform prior approach is much less sensitive to changes on the feasible parameter range that you're looking at. At this point, I just want to break off and then talk a little bit about Stan and bugs and jags. So if you're using something like Stan or bugs or jags, and you've got a random variable x that's normally distributed with mean, mu, and standard deviation sigma, you write a statement like that. And in 2014, when I was doing my PhD, I was working on a model that had a strange likelihood function, but some elements of the model were fairly bog standard. So there I was, I was writing in bugs, and I dutifully defined my data, and then I defined my parameters with priors, and then I got to the bit where I had to link the data to the parameters, and I wrote the equivalent of x tilde, and then I thought, and now what do I write? The distribution is custom. It's not implemented in the bugs language. It's just this distribution it's a density function that these authors themselves sort of came up with. And that got me Googling of how do I implement a custom distribution in bugs? And I don't know if it's possible. All I know is that I gave up before I found out, because when I was looking, I started hitting around Stack Overflow posts or whatever that were talking about Stan. And I discovered that in Stan, you can do it quite easily. And it's all down to this reserved keyword target, this hidden variable target. When you say that x is normally distributed in Stan, what you're effectively saying is to increment the target variable by the logarithm of the probability density function for my data x subject to mu and sigma by the normal law. Now, that's one aspect that I wanted to pull focus to. The other is that you can define custom functions to make your calculations easier. And one of those can, of course, be a prior. So up in the functions block of your model, of your Stan file, you can write a function to define your funky prior distribution. And really what goes on in here is your business. You can get up to anything you want. You can implement the triangle prior or triangle distribution, whatever. But having done something like that, it's then really easy to using this target keyword to implement. You just take, you fire in, you call your prior distribution, and you take its log and you increment target that way. And then, hey presto, you've implemented a custom probability function, either a likelihood function or a prior. So this flexibility was crucial. It let me in 2014 finish the model I was working on. And when I came around to working on these functional uniform priors, and I knew that I was going to derive this strange distribution, it was going to be easy to implement it. And this is exactly how I did it. I'm going to give a few words on some other dose response models. So here's 4 models I'm going to talk about in this talk. And they're broadly arranged from simplest to most complex. I've given them all their names here. The power model. So we talked about the Emacs model already. The power model, as you can see, is very simple. It just raises the dose to a power. Moving downwards, we've got a logistic model, and how it got its name is obvious. We've got this classic sort of logit function going on here. And perhaps most complex is the beta model, and that has elements of the beta PDF down here, so you can sort of understand how it's got its name. Now, the similarity with all of these models is, of course, that they each have this θ0 intercept parameter and this θ1 gradient parameter, in which each of them is linear. So I'm going to kind of ignore each of those, but the way in which they vary is via their non-linear parameters. And as we move down, they generally, they're getting higher parameterizations. So there's 4 models. Now, what I'm going to do just to illustrate each of those is to fit each of those models to that same data set that I illustrated right at the start of the talk with the red dots when I was demonstrating that sigmoidal shape. If I fit each of those 4 models, I get these lines of best fit here. And what I find incredible about this slide is that each of those lines considered in isolation looks plausible. So, each of them sort of seems to be pulling out some aspect of the data. And I look at the Emacs one and I go, yeah, we've got this decelerating curve. That looks fine. If somebody gave me that, I'd accept that as a pretty good fit. But then you see the logit and think, oh, actually, yeah, that's better. That's quite convincing. And then the beta one, it has this up and down. There could be biological situations where that kind of relationship is plausible. And that also does seem to be playing out in the data. So I think this slide sort of shows you how your mind can play tricks. But that's an example of 4 models of increasing complexity fit to exactly the same data using these methods. Just to say a few more words on model fitting and computation. So like we said, I work for a pharmaceutical company, UCB, and the team I work for there is called SESI. And so the package I've written is called sesi.dr, and SESI, obviously my team name, and the .dr refers to dose response modeling. Now, this is an internal package. It's not on CRAN. It's not on GitHub. It's just on an internal server at my company. And I sort of named it this because I can envisage that over the years I work there, I'm going to write probably a suite of R packages. And that's the naming pattern I'm going to use. But you can see now, it is my hope that this will eventually get onto CRAN, but I've got a lot more testing and a few sort of sign-offs to undergo to do that. But really, the model fitting functions I wrote in the package sort of work like this, and that you give it a data set, you tell it some upper and lower bounds for some the parameters in the model, and you use this Boolean FUP for functional uniform prior equals true to use the functional uniform prior, else you can set it to false and get a regular uniform prior. I didn't actually get into the complexity of what other different prior types we might want. At the minute it's just those two. Having written those model fitting functions, and you get back an object, and then it's easy enough to just write some R generics and to plot some produce some convenient plots. But of course they're just ggplot objects, so you can sort of, using the standard way, append on more and more layers, as I do here, to just to drop in the raw data behind the line of best fit. So writing the SESI DR package, a colleague and I at UCB each derived the exact algebraic expressions for the functional uniform prior densities for those 4 model types. And then, I came to write them all down in Stan, and using the custom probability function method that I illustrated. And then, I'm an R user, so I use RStan. I offload the posterior sampling to RStan. And of course, if you've got like a suite of .stan files and you want to put them into an R package, then that's made a lot easier by using the RStan tools package there. Having fit the model, I then have to munge around with the posterior samples, put them into, don't necessarily want them on the parametric scale. I want to go back to the functional scale. And MatK's tidyBayes package makes that really easy. And of course, like I've sort of said, there's object-oriented sort of implementation via S3 and R, and that makes it easy to do things like ggplot plots. So really, this is sort of spanning lots of the tidyverse and the RStan ecosystems. So now, having introduced all that, I'm going to answer the question: why on earth would I use functional uniform priors? What's in it for me as someone who analyzes data? I did a simulation study. So this is the scenario. I assume that we're going to have 5 doses under investigation so I assume they've been scaled down to 0 to 1. And I assume data generating models that correspond to each of those 4 analysis models that I'm interested in. So I assume scenarios where I generate outcomes subject to the power model, the Emacs, the logistic, and the beta. And then what I do is that I fit each of those 4 models to data sets from each of those scenarios. I actually do it a couple of times. I do it once. I simulate a data set, and then I fit a model using the functional uniform prior. Then I fit another model using the regular uniform prior, and I have a look at the inferences. And I investigated different sample sizes, so 10, 20, 30, 50, and 100 patients per dose. So of course, in a 5-dose scenario trial, that corresponds to total sample sizes of 50, which is about right for an early phase trial, all the way up to a total sample size of 500, which would be really big. And then, so that's those are the scenarios. Then obviously do it lots of times. So how many times? Well, when the per dose sample size is 10, 20, or 30, I managed to calculate 10,000 simulated iterations, but only 5,000 each when the sample size was either 50 or 100. And that was simply because of the amount of time it was taking to fit all of these models. So execution is cheap, but it's not free. So I sort of said 5,000 is enough for those 2 scenarios. Okay, so I've got now 4 scenarios to talk about, and there's 4 metrics that I want to talk about too. So I'm going to talk about 1 metric in each of the scenarios. The way I've paired those up, you'll just have to trust me, is just fairly random. I just sort of did it as I was doing it, but here we go. So here's the first one. I want to talk about the mean absolute error. This is in estimating the true dose response curve, okay? And this is in where the true data generating process is a power model. Now, of course, I've got plots here for each of the 4 analysis models. And of course, we'd expect the power model being fit to power model data to do particularly well. And it kind of does. If we look at the lowest mean absolute error from any of these, it's this point here, which is the highest sample size for the power model. So that kind of marries up with our intuitions. The Emacs model does pretty good. It's another is that convex or concave? It's another one of those type of models, and it it's fairly similar, so it does well too. The logistic model tends to struggle a bit, and the beta one shows a pretty wide range of performance. But really, the interesting part of these plots is the distance pairwise between each of these dots here. So it's the vertical distance between the mean absolute error if I estimate using uniform priors versus functional uniform priors. And what we can see is that in every one of those points, the mean absolute error for all of the sample sizes, for all of the analysis models, the mean absolute error is lower using the functional uniform priors than the uniform priors. The next thing I want to talk about is coverage probability. So this is the probability that the estimated response interval contains the true value. And I'm just using 90% intervals here. Now I'm talking about this metric in the Emacs scenario. So once again, the Emacs model being fit to Emacs data tends to do very well, or at least the functional uniform prior model does. You can see that the coverage probabilities are very close to the nominal value when I use the functional uniform priors. They're not so much when I use uniform, particularly so at the low sample sizes. Now, of course, it's the lowest sample sizes that are most likely to be used in a trial of this or a study of this ilk. We tend to have smaller sample sizes rather than huge ones. And you can sort of see that it does take a really big sample size to actually get parity on those two models with respect to coverage probability. So that's when the analysis model matches the data generating model. Those off diagonal pairs, if you like, when the analysis model doesn't match the generating model, you can see that as sample size increases, the coverage probabilities decrease. So where the model's getting swamped out by data that just disagrees with it. But really, again, coming back to or emphasizing the contrast between uniform and functional uniform priors, in each occasion, pretty much, we're closer to the nominal level using the functional uniform priors, even if in absolute sense, we're actually not particularly close to it. In a relative sense, we're always closer using those functional uniform priors. Third metric I want to talk about is bias. This time I'm going to talk about the logistic scenario, and it's a bit of a mixed bag here. So the logistic model in the logistic scenario is the one in which the functional uniform priors provides less bias than the uniform priors. But that actually flips when you go to the scenarios where the instances where the analysis model and the data generating model don't match. You know, instances here, the average bias is kind of similar. It's less similar in other places. Notably, even at the mega sample sizes, even when the analysis model matches the data generating model, there's always a little bit of residual bias, even if a residual upward bias, even if in an absolute sense it's pretty small. That y-axis there is pretty zoomed in. Fourth and finally, I wanted to talk about the length of the credible intervals. And really, there's not much to say here at all. The functional uniform priors are going to have, I'd say, a larger effective sample size because they're more informative. That doesn't really translate to tangible or noticeable changes in the interval widths. So by that metric, the two methods are pretty similar. So just to round up to summarize those points, using the functional uniform priors compared to regular uniform priors, we see lower errors in estimation, closer to nominal coverage probabilities, similar to slightly higher biases, and similar interval lengths. Going back to Bornkamp's paper, this paper he wrote in 2012, he did a simulation study there too. He didn't use Stan. He didn't actually use bugs either. He used he wrote his own MCMC stuff. You know, his simulation study was a little bit sort of smaller. You know, I've got the benefit of 10 years of extra technology on my side, but he investigated a power model in power and Emacs scenarios just at a single sample size, comparing those functional uniform priors to regular uniform priors. And he too observed lower errors, closer to nominal coverage in intervals, and similar interval lengths under the functional uniform priors. Now, he also looked at Jeffreys priors. So he actually had three schemes going on. And he found that the Jeffreys priors produce similar performance. There's a few missing words there. That should say to the functional uniform priors, not similar to the regular uniform. So Jeffreys and functional uniform priors approaches were fairly similar, he said. But he did offer quite sort of pointed criticism of the Jeffreys prior approach in that he said it violates the likelihood principle, and that's awkward when, especially in something like an adaptive trials, where you can't specify those analysis points up front, and so you're sort of in a bit of a chicken and egg situation. So for that reason, I didn't myself look at the Jeffreys priors, and my study was already big enough. So it was quite welcome to be able to cleave out one avenue of variability. So there's a lot of coherence with between Bornkamp's findings and my findings on a sort of wider model scale and different sample sizes. So some conclusions are that implausible uniform priors can really hurt your inference, even with large sample size. And functional uniform priors in this nonlinear regression setting that is so common in dose response modeling, I think they constitute a good starting point for specifying priors. I know that the idea of automatic prior specification is somewhat contentious in Bayesian circles, but if you're going to have like a starting point, surely this is a better starting point than pure ignorance on the parametric scale, because of course, as we've seen, there's a lot of information. You could end up conveying a lot about the functional form by trying to be uninformative on the parameter scale. Just a few slides on future plans. I'm going to try and get this published. I should stress this is all unreviewed. It's not been to a journal yet, so this could all be wrong. But part of the simulation study is kind of me satisfying myself that I've implemented all this stuff right, and it all looks plausible, I think, thus far. So I've written a manuscript, and I hope to have it on archive at some point, and I hope to get that submitted for peer review too. Like I said, maybe the functions in the R package could make their way onto CRAN as well. But working for a pharma company is a little bit different to working in academia, so that there might be a few sort of sign-offs to undergo as well. And just one slide on a theoretical extension. So in real situations, of course, we don't know the form of the data generating model, and so what we tend to do when confronted with a data set is to fit lots of models, and we use kind of heuristic methods, if you like, to choose between those. This one is slightly more complex and therefore asks more of the data, but it seems to fit it better, and I might move forward with that as my nominated model. But to a Bayesian, that might seem undesirable. We might instead want to say, well, I could maintain the belief that all of the models are right to some degree, if you like, and think of my final model as being a weighted sum or a weighted stack of each of those component models. And of course, that's the type of thing that you can do in the Loo package, another package right out of the RStan ecosystem. And I've actually undertaken a few proof of concept studies using Loo and the four models that I talked about at the start. So what I did was to say, okay, let's assume one of the data generating models, and then let's analyze it by fitting the four models and dropping them into Loo, and then doing the posterior as being a weighted sum of the component posteriors. And I ran that, and for quite high sample sizes, admittedly, you can actually quite reliably spot when the true data generating model is one of the constituent models. So in that model closed space, you can actually recover that information and end up getting 100% allocated to the true model. So that was nice. What I also saw, and this was an early result, and I need to go through and check it, but I then sort of said, well, what if the data generating model itself was this weighted sum of various different submodels? Let's say the true curve is 10% power model plus 50% logit, and I analyze it using this model ensemble, and to my surprise, I actually managed to recover those, get quite close to those weight. And I say to my surprise, I kind of assumed that model would be non-identified, but perhaps in that particular example it wasn't. Like I say, this is quite an early result, but that to me seems like a fruitful avenue to go down that abrogates this slightly uncomfortable need to identify just one model and then to pretend that that's my guy. Okay, so that's brought me to the end of my slide deck. I did all of this work in collaboration with two fellow methodologists, UCB, Fattini and Andy. And of course, like I said, I made great reference to Bjorn Bornkamp's papers when I was exploring this work. Those are there, and like I've said, I've got a manuscript that's just basically in draft. At that, I'd say thank you for your attention, and I'll leave my slides up, Eric, but I'll hand back to you.
Thanks, Kristian. That was great. Let me ask a couple of questions. So the first one is from Elizaveta Semyonova, who asks, have you had to deal with bi- or multiphasic dose response curves?
The short answer is no. Maybe a slightly longer answer is not yet. No, I haven't got down to biphasic. What is biphasic?
You want to type in what you mean by biphasic?
Oh, I see. Like having a good response, and it might work and then come back. Okay. No, I've not gone into that kind of complexity. And if that's what's in store for me, then I'm already worried.
All right. Let me ask perhaps a naive question. So one of the Sergey just said U-shaped.
So I could say a bit more on that. So the U-shaped, yes. The I don't have any real data to back up a U-shaped dose response curve, but I do know that in, for example, the immunotherapies in cancer, there is a growing body of evidence, or belief rather, that there could be points at dosing where you know outcomes start to degrade having peaked. This beta model here actually does this unimodal shape, if you like, of this up and down.
All right. So the next question from Jacob Fiskel is that I would be interested to hear if you think these functional uniform priors have any promise in phase 1 setting with a CRM design with 2-parameter logistic model.
Yeah, I do. I think I looked at so that what I'm going to do, I'm going to go back to one of my slides. If you look at the classic CRM, or one of the easiest CRMs, is what they call the empiric model, and it's actually this power model if you ignore the intercept and the gradient. It's just this bit here, x to the theta 2. I did actually fit a few power models using a functional uniform prior rather than a normal prior. So the package DF CRM in R, which was written by Ken Chung, he puts a normal or a log normal density on this power parameter, and I looked at it, I compared it to a functional uniform prior, and you know, as you might well be, you probably wouldn't be surprised to hear that in a model that's that simple, it doesn't make the world of difference. You know, the probability of correct selection, which tends to be more the focus of phase 1 trials that use CRM, the probability of correct selection was fairly similar. Yeah, sure. You know, I think that the functional uniform priors are a more plausible starting point than the normal or the log normal ones. And I think that particularly, so I think the question mentioned the 2-parameter models. I mean, that's probably getting on for, you know, the type of complexity that would benefit from this. So yeah, that was the long answer. The short answer is yeah, sure. I think there's scope to explore it there.
Cool, thank you. So let me ask the following question. So, you know, typically the way we deal with this kind of complexity in nonlinear models is by like simulating from prior predictive distribution and sort of seeing what kind of things we observe, right? And then kind of, you know, playing with that. It's I guess a kind of a heuristic method or experimental method. You know, this is sort of more principled approach for the uniformity of this functional space. Now, if I had a preference for some kind of a functional space that's not uniform, but I wanted but still had an opinion on preferring some functional forms over the others, do you think that this has a sort of an extension into that world? You know what I'm trying to say?
Yeah, sort of. I think so tell me if I've misinterpreted. I think that the answer to that is the stuff I was talking about just at the end of having this model stacking. That's the way that I would seek to combine these models. I would want the most complex model to have embedded within it as special cases each of the simpler ones, and then really let the sort of model fitting tell me the answer or the favored approach. But what you mentioned about the prior predictive. So interestingly, I collected a bunch of phase 1 data sets on a different project and wanted to fit models to each of them because I was testing a hypothesis that response rates in phase 1 trials don't tend to increase in dose, but toxicity does. And there's a fairly obvious implication for that if that's a wholesale true thing. And so I had all these siloed phase 1 data sets and I wanted to analyze them. I fit using a BRMS, I fit Emacs models to them. And of course, I hadn't studied functional uniform priors then. I had to provide priors. And I sort of felt like I spotted straight away that, you know, uniform priors were just going to be dead. But I did exactly what you just sort of said in that I sampled, I sort of generated prior predictive curves and then just looked for what kind of made sense or what gave the spectrum of functional forms that I believe were believable. And of course, that felt deeply unsatisfactory because I know what I was doing kind of made sense, but there's me trying to write it on a paper in the methods section, and I'm thinking a peer review is just going to tear this a new one because like it's basically me going, I stick my finger in the air. So I guess this one appealing thing is this adds a level of formality to that. What I should now do, of course, is go back and find the prior I ended up choosing and see how far different it is to the functional uniform prior. I'd probably be shocked.
Yeah, that makes sense. So Sergey Aksenov is asking, I think, like a practical question, which is, what's your experience with convergence of Stan using functional versus other priors?
Really apt question. So this was a thing for me doing this work, is that, of course, using Stan, you get lots of feedback about divergent transitions. It's apposite that I'm on this model slide. I'm going to zoom in, and what I'm going to say is, generally speaking, any of the sample sizes in my simulation studies, getting divergent transitions was not a problem. It happened maybe like in 1% of model fits. It wasn't a wholesale problem, except the this logit model here. I mean, I sort of feel dumb saying it, but it took me a while to spot that there's, danger lurking here with the θ3 parameter. If your prior allows θ3 to go too close to 0, obviously it explodes, and you get divergency. So, but once you keep that away, the logistic function behaves itself. The beta one is one of the functions I thought I was going to get a lot of problems with. I didn't. It was actually quite well behaved. So just summarizing my answer, not a great deal of problems at all, and there was no difference. I would say on several occasions, actually, just using a uniform distribution on some of these nonlinear parameters would create divergences that would be solved by using this more informative functional uniform prior. So it's a good question, and they help.
That's awesome. Great. I think the last thing I'll ask is that you mentioned that the code is, so far you guys reviewing it, and it's kind of sitting in your area, and you hope it'll find its way out at some point. If someone wanted to go and sort of try to implement this themselves right now, what would you recommend they do? They should read the original paper. Like, what would be the steps?
I think that if they were using one of the simpler models, the power of the Emacs model, say they could read the original paper, they could find out the steps, and they could reproduce. They could derive this density function that I think I put up with relative ease. It would be a fun afternoon. But if they were going to use one of the other ones, yeah, they'd be able to derive this result, fairly simply. But the logit ones and the beta one, they are quite painful. And so what I would say is, get my preprint when I post it, and at least then you'll have density function laid out for you and all of the steps in the supplementary information that show the calculus. So you can satisfy yourself that what I'm saying is right. I checked it on Wolfram Alpha, and I think it is right. And then once you've actually calculated these functions here, then it's quite easy, like I've said, to implement them in Stan. That's one of the sort of the biggest pieces of value I could add, is that I've done the calculus, so you don't have to.
Yeah. That's very helpful. All right, with that, thanks a lot, Kristian, for your presentation. It was great. We'll be back with another talk in February. Everybody have a great remainder of the day. See you soon.
Thanks very much, Eric, for having me on.
You bet.